Here we're going to see another example of a problem that we're going to model it as a linear programming problem, and then we're going to solve it using the graphical method. General description of the problem is as follows. A firm that assembles computers and computer equipment is about to start production of two new types of microcomputers. Each type will require assembly line, inspection time, and storage space. The amount of each of these resources that can be devoted to the production of the microcomputers is limited. The manager of the firm would like to determine the quantity of each microcomputer to produce in order to maximize the profit generated by the sales of the microcomputers. Let's see additional information about the requirement for this problem. In order to develop a suitable model of the problem, the manager has met with the design and production personnel. As a result of these meetings, the manager has obtained the following information. For type 1 and type 2 microcomputers, this information is as follows. Profit per unit for type 1 is $60 per unit, for type 2 is $50 per unit. Assembly time per unit required for type 1 is 4 hours, for type 2 is 10 hours. The inspection time per unit required for type 1 is 2 hours, for type 2 is 1 hour. The storage space per unit of type 1 is 3 cubic feet, and for type 2 is also 3 cubic feet. The manager has also acquired information on the availability of company resources as follows. Assembly time, they have only 100 hours. For inspection, they have 22 hours. Storage space, they have a total of 39 cubic feet. The manager met with the firm's marketing manager and learned that the demand for the microcomputers was such that whatever combination of these two types of microcomputers produce, all of the output can be sold. So whatever computers they can produce, we assume that they can sell it. We want to model this problem as a linear programming problem and then solve it. Here I'm going to solve this problem, model this problem as a linear programming model. Before I do that and you follow, please pause, try to solve this problem on your own. Go through all the steps of modeling, define the decision variables, define the objective function, whether it's minimization or maximization, and then also every constraints that you can find for the limited resources that this company face, and also the non-negativity constraints. And then after you're done, come back to see the solution and how it is solved. So we start off by defining this decision variable. The decision variables are as follows. The company wants to produce two types of computers, type 1 and type 2. So the amount, the quantity of production of type 1 and type 2 are the decision variables. I'm going to say x1 is the quantity of production of type 1 computer, and x2 is the quantity of type 2 computer. Now we need to define the objective function. So the objective, the goal of the manager for this company is to maximize the profit. So this is a maximization problem. Maximizing profit. Now we need to write a function, the profit function, in terms of the amount of production of type 1 and type 2. That means that in terms of our decision variable. This is always the case. Your objective function should be a function in terms of your decision variables. So what is the profit that the company makes regarding the quantity of producing a selling type 1 and type 2 computers? For each type 1 computer, they're going to make $60. So that's $60 multiplied by the quantity of type 1. How about type 2 computers? The profit that they make per quantity, one unit, is $50. So that's $50 multiplied by the quantity of type 2 computers that they make. So 50 multiplied by x2. Let's now go to the constraint. So this is subject to, I'm going to write it as SD, subject to the constraints. One of the constraints that we can think about is the assembly time that they can spend on their production. So they only have 100 hours of assembly time. That means that the amount spent assembling type 1 and type 2 computers cannot exceed 100 hours. So cannot exceed 100 hours. This is on the right side. And the left side is the amount spent producing type 1 and type 2 assembling. Type 1 computers would require 4 hours assembly line. So that's 4 multiplied by the quantity of type 1 computers plus 10 hours of assembly time for type 2 computers. So that's 10 multiplied by x2. So this is for the assembly time. Another restriction that this company is facing is the inspection time. So they only have a total of 22 hours inspection time available. So whatever they spend inspecting type 1 and type 2 product should not exceed 22 hours. Type 1 computers would require 2 hours of inspection. So that's 2 multiplied by x1. Type 2 computers would require 1 hour. So that's 1 multiplied by x2. I'm going to write it as x2. And this is an inspection time constraint. The next constraint or limitation is the storage space. They have a total of 39 cubic feet storage space. So the amount of storage required for the quantity that they produce for x1 and x2 on the left side should not exceed 39 cubic feet. That means B should be less than or equal to 39. Each type 1 microcomputers would require 3 cubic feet. So that's 3 multiplied by x1 plus each type 2 computers would also require 3 cubic feet. So that's 3 multiplied by x2. So this should be less than 39 cubic feet storage. And the last constraint is the non-negativity constraint. So that means that x1 and x2, the quantity of type 1 and 2 microcomputers should not be negative. So x1 and x2 should be positive. That means greater than or equal to 0. All right, so this is our model. We define the decision variables and then objective function, and based on that, then we develop the constraints for the resources. Here you can see a typed version, a more legit and clear version of the model that we have. So we have the two decision variable, x1 and x2, the quantity of type 1 and type 2 production of computer 1 and computer 2, type 1 and type 2, and the objective is to maximize profit, and profit is $60 per unit of type 1, so 60 multiplied by x1 plus profit based on production of type 2 computers, which is $50 per unit, so that's 50 multiplied by x2. So the objective is maximizing 60x1 plus 50x2. And next we have the constraint here, so subject to our constraint. The first constraint is assembly constraint. So the total assembly they have is 100 hours. So whatever assembly hours spent on the computers should not exceed hundreds. So that's 4x1 plus 10x2 should be less than 100 hours. For inspection, they only have 22 hours of inspection. So 2 hours for per type 1, 1 hour per type 2. So that 2 multiplied by x1 plus 1 multiplied by x2 should be less than 22 hours. For storage, they have 39 cubic feet limitation on storage. Each type 1 requires 3 cubic, type 2 requires 3 cubic. So that's 3 multiplied by x1 plus 3 multiplied by x2 should be less than equal to 39 cubic feet. And the last constraint is the non-negativity constraints. And here's the model. Our model is complete. Here we're going to use the graphical method to solve our LP model. Since we have only two variables here, two decision variables, x1 and x2, we can actually do that easily. All right, so the first step is to plot the axis, the x-axis and y-axis, the two decision variables that we have. So this is the two axes. Suppose this is x1, the amount of production quantity for type 1, and this is x2, quantity of production for type 2 computers. So the first constraint that you can enact here would be the non-negativity constraint. x1 and x2 should be non-negative. And this means that anything on the left side of x1, this, if suppose that this is 0, the intersection between the two axes is 0. So on the left side, the x1 is negative. So we're gonna ignore that. That's not going to be part of our feasible space. And also below 0 for x2 is negative. So we're not going to consider this either. This means that our feasible space so far is this right here between the positive side here. So as you see here, the x1 axis is the quantity of type 1 here, x1, and this is x2, quantity of type 2. And this is the intersection is x1 and x2 both are 0. So on this side x1 is positive and x2 is positive. So this is our feasible space, area of feasibility so far. And these two are non-negativity constraints for us. This line and these lines are non-negativity constraints for us so far. The next step is to gradually add the other constraint that we have, the assembly constraint, the inspection constraint, and the storage constraint. These are the steps for plotting the constraints. The first step is to replace inequality sign with equality sign for each constraint. Then you're going to get an equation of a line, a two variable line. Then you need to find determine where the line intersects with each axis. That means that you need to find 2 points for this line and then connect the two dots together to find the straight line for the equation or inequality, the constraints. And then indicate by shading which side of the inequality is the feasible side for you, the feasible side for the constraints. And then you have to repeat this as step 1 to 4 for each other constraint. We're going to do this for the three restriction limitations that we have for inspection, for assembly, and for storage. So we are going to add other constraint to our plot here. So we had x1 and x2. I'm going to plot it again here. x1 here, x2 here, and this is the 0 point. The first constraint is for the assembly requirement or limited resources, and that's 4x1 plus 10x2 should be less than equal to 100. The first step, as we saw previously, is to actually replace this inequality sign with the equality sign, so that we can, now this is an equation for a line, a two-dimensional line. So we can plot this line, a straight line. Okay. So to plot this, we need to find two points of this line. The best way to do that is find, usually to go with where these lines would actually cross-section the two axes x1 and x2. So I'm going to set this as 0. If this is 0, then 10x2 is equal to 100. So that means that x2 is equal to 10. So x1 0, x2 10, x1 0, and x2 10. Suppose this is here. This is 10. So this is one of the points for us. The other point, I'm going to set x2 equal to 0. So x2 equal to 0. This is 0. Then x4, x1 equal to 100. This means that x1 is equal to 25. So x1 25 and x2 10. It's going to be here, for example. 25 x1 and x2 is 0. So now we have these two lines for this inequality. I'm going to plot it here. I'm going to connect this line with that line. All right. The next step to see which side is the feasible side for this constraint, here or here. So to do that, I'm going to find a point in one of these sides. For example, this side. This is 10, suppose this is 10. So this point here is x1 10, x2 10. I want to see if this is actually in the inequality. So first we need to convert this inequality into equality here. So this is less than 100. Now we're going to put this point in this inequality to see if this is less than 100. So 4 multiplied by x1, that means 4 multiplied by 10. 4 multiplied by 10 plus 10 multiplied by 10. So that is equal to 40 plus 100. That's 140. 140 is not less than 100, right? So this means that this point is not in the feasible space. So this side must be our feasible space. This is our feasible space. So this is our first inequality. This is 4x1 plus 10x2 less than 100. Next, we are going to add the next constraint, which is for the inspection time restrictions. All right, so this is our assembly time constraint, and we have our feasible region. Next, we are going to add the inspection. The inspection constraint is as follows. 2x1 plus 1x2 should be less than the total inspection time available, which is 22 hours. So the first step is to change this inequality sign into equality. So we're going to get a line, an equation of a line. Next is to find two lines for this equation line, 2 points. Generally, we're going to go with the intersection of this line and the two axes. So I'm going to set x1 equal to 0, x1 equal to 0. That means x2 is equal to 22. So x1 equal to 0, x2 equal to 22, somewhere here. And next I'm going to do the same for x2. x2 equal to 0. This means 2x1 equal to 2020. That means x1 is equal to 11. So x1 is equal to 11. x1 equal to 11 and x2 equal to 0. So that would be somewhere here. All right, now I'm going to connect these two points to get the line. So this is our line. Next, we need to know what part of this is feasible. This space or this space. So let's first turn this into inequality. This should be less than equal to 2020. One point that we can actually set and test here is 0, 0. So 0, 0, I'm going to test it whether, because it's on the left side. 0, 0, that would be 0 plus 0, that's 0, which is less than 2020. So this actually checks. So this actually is our feasible space. So our feasible space is on the left side here. Okay. You have to be careful about now. You have to follow the commonality of feasible space. So our feasible space for the inspection time is this space here. However, this line, our previous assembly line, the space that you see here, this space is not feasible for assembly time. So we're going to get rid of that. And our only feasible space would be actually here, the common area. This would be the blue shaded blue. It would be our common feasible space for the two constraints. All right, so this is our assembly line, this line, and this line is our inspection, and this is our common feasible space so far. All right, next we need to add the other constraint, which is a storage constraint. All right, so this is our feasible space so far. Next we're going to add the storage constraint, and the storage constraint is as follows. 3x1 plus 3x2 should be less than equal to 39 square feet. So we're going to follow the same procedure. We're going to first transform this to an inequality or a line, a formula for a line. So I'm going to replace this inequality by a line equality. So this is 3x1 plus 3x2 equal to 39. Now this is formula for a straight line. We can find the 2 points here that intersect with the two axes x1 and x2. So I'm going to first set this as 0, x1 equal to 0. That means that 3x2 equal to 39, or x2 is equal to 13. So x1 equal to 0 and x2 equal to 13. Somewhere here. 13. Next, I'm going to do the same for x1. So I'm going to set x2 equal to 0, and that's 3x1 equal to 39, or x1 equal to 13. So that's this line over here. Now I'm going to connect these two lines to get these 2 points to get the constraint line. somewhere here. All right, so this is our line. Now we need to test what side of this is actually the feasible space for this constraint. So I'm going to replace the equality with inequality. So this is going to be less than equal to 39. Then I'm going to test 0 and 0, for example, which is on the left side of this line. So 0 and 0 would be 3 multiplied by 0, that's 0, plus 3 multiplied by 0, that's 0. That's 0 less than 39. Yes, that's true. So that's feasible space. So our feasible space for this line would be on the left side of this. But I'm going to go with the common areas so far. So this would be here. This would be our feasible space. Note that this is not the feasible space right here. This is not the feasible space. So this is what we get. We implemented the three inequalities, the three constraints, and our feasible solution is shown here by the shaded blue area here. Here. Now the next step is to find the optimal solution here. The optimal solution, as we learned, we can actually plot the objective function for within the feasible solution and then move it to the extreme so that it would only touch the one point, kiss the one point one point or a line with the feasible space. Beyond that, it would be out of the feasible space, and that would give us the optimal solution. Or we could go with the cornerstones, as I mentioned here. So according to a theorem, the optimal solution for a linear programming would always occur at a corner point or extreme point here. We have 5 extreme points here. So what we can do is we can find the coordinates for these extreme points and plug it into the objective value and find the profit based on these points. And whichever gives us the highest profit, that's going to be our optimal solution. Now that we have plotted the constraints and I have figured out the feasible space or the common intersection or a space that it's feasible and would satisfy all the constraints, the next step is to plot the objective function. So the logic is similar to what we have for plotting the constraint. Because there is no equal sign for the objective function, the objective function was maximizing 50x1 plus 60x2. So as you see here, there is no equation or equality sign here. So what we can do, we can simply set the objective function to any quantity in the feasible space and find the profit line. Profit line actually is a line that for each point on that line, we're gonna for each point, it means that for each x1 and x2 quantity, we're gonna make the same profit. This line is also called the ISO profit line. Every point on the ISO profit line represents a combination of the decision variables x1 and x2 that would result the same profit. And after we're having the ISO profit line, we're gonna move it so that according to the increasing direction that would increase the objective value here, because we are solving for maximization problem. If we were solving for a minimization problem, we would actually move it to the decreasing direction to minimize the objective value. And we're going to move it so far that it would one step before we actually move to the infeasibility space. So let's go ahead and apply this step for our problem. Okay, so we have our feasible solution space here, and we want to plot the objective value or the ISO profit. So what we can do is we can actually find set it to a value and then find the ISO profit. So for example, for these two lines, x1 equal to 5 x1 equal to 5 and x2 equal to 0. So this point right here, for this point, x1 is equal to 5 and x2 is equal to 0. So that means that the objective value for this point would be profit for x1 equal to 6, 5 actually, and x2 equal to 0. So for this, the profit would be 60 multiplied by 5, which is 300, plus 50 multiplied by 0. So that would be, the profit would be equal to 300. So that's one line. We need to find another line, another point, which the profit is also equal to 300. One point actually we can find in the on the intersection for the x2 axis here, and that is x1 equal to 0 and x2 equal to 6. So for example here, this point x2 is equal to 6 and x1 is equal to 0. So the profit for this would be 60 multiplied by 0 plus 50 multiplied by 6, 6 multiplied by 50, 50 multiplied by 6, which is equal to 300. So the profit would be the same. Now if I connect these two lines together, this is the ISO profit, and for each point on this line, the profit is going to be 300. So this is the line. Now we have the ISO profit line. We're going to move this ISO profit line to either this way or this way, whichever direction that would actually increase the objective value, because we want to maximize the profit. So we're going to move it in a way that would increase the profit. Right now the profit is 300. So if I said, for example, in this direction, the left direction, this point 0 and 0, for 0 and 0 the profit would be 0. So that means that we shouldn't move it to the left, we should move it to the right direction. So we're going to move it to the right direction until it would touch or kiss the feasible space right before it actually get out of it. At that intersection is going to be our optimal solution. So we're going to move the ISO profit line further away from the origin, and you have to notice that ISO profit lines are always parallel. So whenever you move it, the next one is going to be parallel to this one. So let's go ahead and move it further to the right in this direction. That would increase the profit. So for example, if we move it further as this point, we're gonna get this line as you see here. This is our new ISO profit line. And for this ISO profit line, the profit is 600. But still, it has, as you see here, our profit increased from 300 to 600, almost actually doubled, exactly doubled. But it still is within the feasible space. And also, the other point that I want you to notice is that these two lines, the orange lines, are parallel. So either profit line must be parallel. We still have room to move this line further to the right. So let's do that. Let's move it to the right. I moved it too far, as you see here. This line, the profit is $900, but the point is this line, which is also in parallel to the two other orange line, the ISO profit line, is every point here is actually on the infeasible space, is not in the feasible space, because the feasible space, as you see here, the feasible space is here. This is our feasible space. And this line is outside of the feasible space. So although it would produce a higher profit, it is not possible. It's not within our feasible space. So that means that we need to go back a little. So we need to move this a little bit to the back. And what we're going to end up here would be somewhere that is going to touch this point here. So this would be our the extreme point that the ISO profit is going to touch the feasible space, so that if you move it a little bit to any further, it would actually get out of the feasible space, and that would be that point, that corner point would be our, or extreme point would be our optimal solution. All right, let's find the optimal solution here. So where is the optimal solution? The optimal solution, as I said before, occurs at the furthest point for a maximization from the origin of the ISO profit that we have at $300 here. And we're going to move it further such that it would still be touching the feasible solution space. As you can see here, this is this line, this orange line, which is in parallel to all of our other ISO profit. This is our optimal solution, because and this is going to be the last point that the ISO profit would touch the feasible space. This line, this point. So we need to find this point. But how to solve this? How to find this point? We want to find the value of x1 and x2 for this point, the optimal solution. How do we do that? All right, so the optimal solution, or this cornerstone, this corner or the extreme point, is always at an intersection of at least two constraints. So as you see here, this point is at the intersection of these two lines. This line, this constraint, and this constraint. So what we are going to do is we're going to solve a system of two equations here for the two constraints. And remember that these two lines touch each other. That means that they have intersection. So let's go ahead and write the system. The one that I highlighted by yellow is for storage, and the one that I highlighted by red is for inspection. So I'm going to write it again here, the two constraint here. For inspection, it's 2x1 plus x2 less than equal to 22 hours. And for the storage is 3x1 plus 3x2 less than equal to 339. But here we are dealing with a line, as you see here. So I'm going to convert this to equality. This is equal to, and this is equal to. Now, at this point, the intersection here, at this point, the two lines intersect. That means that the values for x1 and x2 are actually equal. So you should remember from algebra that how to solve actually for x1 and x2 in this system of two equations that you see here. So I'm going to do it very fast. So once I'm going to get rid of one of the x1 or x2, what I can do is here I have 3x2 and here I have x2. So what I can do is to multiply the first equation, both sides, by -3. So if I do that, I'm going to get negative 6x1 minus 3x2 equal to 22 multiplied by -3, that's -66. So now I'm going to ignore this equation as I replaced it with this equation. And I'm going to consider these two now. I'm going to write it here. So now we have these two equations in green. What you can see here is we have negative 3x2 here and 3x2 here. So if I add these two up, I'm going to get 0. I'm going to add the two sides of equation. So if I add this, I'm going to get negative 6x1 plus 3x1. That's negative 3x1. And I'm going to add these two also, negative 3x2 plus 3x2. So this is going to be 0 plus 0 is equal to, I'm going to add the two sides of the equation here. So that's negative 66 plus 39, which is minus 27. So this is minus 27 here. So this means that 3x1 is equal to negative 27. Solve for x. x1 must be 7. So x1 is 7. Now that we have x1, we can actually put it in any of these equations to get x2. So for example, I'm going to put it here. So that would be 3 multiplied by x1, 3 multiplied by x1, which is 3 multiplied by 7. So that's 27 plus 3x2 equal to 39. And if we solve for this, 27 is going to be 39 minus 27. That is 12. So I'm going to write here 12. So 3x2 is equal to 12. This means that x2 is equal to 4. So I have it now. We have x2 equal to 4 and x1 equal to 7. I'm going to write it on the left. x1 equal to 7 and x2 equal to 4. So let me clean everything else. All right, so this point, the coordination for this point is x1 equal to 7 and x2 equal to 4, and this is our optimal solution. So I'm going to put a star above these 2 points, which indicates that these are special because these are optimal solution. And we can actually find our optimal value. The maximum profit would be equal to 60 multiplied by 7 x1 star plus 50 multiplied by x2 star, which is 4, and this is equal to 420 plus 200, which is equal to 620. So the maximum profit is $620. $620. That's the maximum profit that this company can have.